पवित्रवतु ॐ चोदयेत्रे सूनृतानां चेतन्ति यज्ञं दधे सरस्वती।
So today I will be taking the topic aromatic electrophilic substitution reactions. Now you know that this topic is a very important topic in the synthetic organic chemistry. Mainly because with the help of this class of reactions, you can introduce a number of functional groups such as the nitro group, the sulfonic acid group, the halide ion or sulfonium ion, sulfonic acid group, the Acylation cation, and so many other groups can be introduced using this class of reactions. And you find that once these functional groups are introduced, then you have a variety of uses as drugs, dyes, or any other consumer products for that matter. Now I will be discussing this topic in three parts. The first thing is introduction to the topic. The second one is the mechanism involved, and the third one are the most important types of reactions which belong to this class of reaction. Now coming to introduction, we will understand what are these terms. You know that the simplest aromatic ring or aromatic nucleus is benzene. Now what is the structure of benzene? In benzene you have a sigma framework of 6 carbon atoms which are bonded to 6 hydrogen atoms, and there is a pi cloud of electrons above and below the benzene ring. You have a pi cloud of electrons above and below the plane of the sigma framework of the benzene ring. Now this pi cloud of electrons, although they are belonging to a stable aromatic nucleus, in spite of that they are available for reaction with a very strong electrophile. Now what are electrophiles? Electrophiles we know are electron deficient species. Now as they are electron deficient, they are electron loving. So therefore they can easily react with the benzene ring which is having a pi cloud of electrons. Now the examples of these electrophiles could be alkyl carbocation, a nitronium ion, Acylation cation, or you can have SO3 which can act as an electrophile, to name a few of these. Now the aromatic ring undergoes substitution reactions with the electrophile and not addition reaction, as is undergone by the alkenes. Alkenes contain double bonds and they react with the electrophile to form a carbocation. A carbocation reaction intermediate is generated in this reaction. Then it reacts with a nucleophile which is available in the reaction mixture, and that gives us the addition product. So in case of alkenes, the electrophilic reaction proceeds giving us the addition product. When an aromatic ring, aromatic nucleus reacts with an electrophile, again a carbocation is generated because a double bond opens up and forms a sigma bond between this carbon atom and the electrophile. So the octet of this carbon atom, which is adjacent to the carbon atom which is attacked by the electrophile, is incomplete, and therefore there is a positive charge there, and thus an arenium carbocation is generated. Now this can lose a proton by reacting with a base, and the electrons which hold this proton, they can enter the ring, and aromaticity is restored in this case. So you get a substituted benzene ring. Another pathway could be that it reacts with a nucleophile, as in case of the alkene. In case of the alkene, this was the carbocation formed. Later it reacted with the nucleophile and gave you the addition product. Now here, if it reacts with the nucleophile, it can give you the addition product. It is found that the benzene gives the substituted product rather than the addition products. Now this is because the substitution product is the more stable aromatic compound, whereas the addition product is the unstable non-aromatic nucleus. This can be very easily explained by the energy profile diagram or the reaction coordinate diagram, wherein we plot the progress of the reaction versus the free energy. The energy profile diagram looks something like this. Here you start with benzene and the electrophile. Here will be the formation of the carbocation, arenium carbocation. This is transition state 1, and here lies the transition state 2. So the benzene ring has to overcome this barrier of transition state 1 before it can form the carbocation, arenium carbocation, and it has to cross the second barrier before it can give you the substituted product. Now you find, when you compare the energies of benzene and substituted benzene, that the delta G is almost 0, and therefore this reaction proceeds very easily. On the contrary, if you see the addition product, you will find that there is a lot of energy difference, and this reaction is highly endergonic. The reason is the same, that the product which is formed is non-aromatic and therefore highly unstable, whereas the substituted product is stable because it's an aromatic nucleus which is formed. Okay, so with this understanding of the topic electrophilic aromatic substitution, we move on. What are the 5 most important reactions which belong to this class? The first one, as I told you, is nitration reaction. Second one is halogenation. The third one is sulfonation. Then you have Friedel-Crafts alkylation and you have Friedel-Crafts acylation. Now, when we move on to the mechanism of this reaction, we find that in each of these 5 reactions, the mechanism is, the steps involved in the mechanism is the same. The first step is the generation of the electrophile. The second step is the reaction of the benzene ring with this electrophile. The third step is the loss of proton to give you the stable monosubstituted aromatic nucleus. So, generation of electrophile. You know that electrophile is a short-lived species. So, it has to be generated in situ, that is in the reaction mixture itself, because it is unstable. It will not remain for a long time. The second step is the reaction of the aromatic nucleus, in this case the benzene ring, with the electrophile. Now this results in a resonance stabilized carbocation. I will take the example of benzene plus any electrophile represented by Y. The bond, initially actually the electrophile is attracted towards the benzene ring and it is held on the pi cloud of electrons at a distance and a pi complex is formed. Immediately this pi complex breaks and a sigma complex is formed. How is a sigma complex formed? One of the pi bonds opens up and forms a bond between that carbon and the electrophile. So that is how an arenium carbocation is generated, as we had discussed earlier. And this arenium carbocation is resonance stabilized. Now, how will you generate these resonance structures? By the shift of the double bonds. When the double bond shifts to a new position, the octet of this carbon atom now is incomplete, and therefore this carbon atom will bear a positive charge. Next, I can show the shift of this double bond to another position, and now as this carbon atom is electron deficient or its octet is not complete, it will bear a positive charge. Finally, I can show a resonance hybrid. Now please note that the positive charge has always gone to ortho positions and para positions, but it has never gone to a meta position. So therefore when I draw a resonance hybrid, I will show a circle with the dotted lines. The last step is loss of proton. The loss of proton is brought about by the abstraction of proton by the presence of any base which is present in the reaction mixture. For example, in case of Friedel-Crafts alkylation, it could be AlCl4 minus, or in case of nitration reaction, it would be HSO4 minus, bisulfate anion. So the base abstracts a proton. In the process, the pi bond is returned to the aromatic nucleus and the aromaticity is restored. What results is a monosubstituted compound. Now since in this step from a non-aromatic unstable reactive species we get a aromatic stable compound, therefore this reaction is fast and this reaction is exergonic. Whereas in the earlier step, from a stable aromatic benzene ring, we are getting the formation of a arenium carbocation, which is a charged species, and therefore this is a slow reaction and it is also a energy consuming reaction. And this is the rate determining step in this reaction. Okay, so as I told you earlier, these two steps, that is reaction of aromatic nucleus with the electrophile and the loss of proton to give you the mono-substituted benzene nucleus. Both of these are common to all the five class of reactions we just discussed. And what differs in all of these reactions is the generation of the electrophile. Now let us go to this step, that is generation of electrophile, one by one. The first reaction, that is nitration. In case of nitration of benzene, we often use nitrating mixture. What is nitrating mixture composed of? Concentrated sulfuric acid and concentrated nitric acid. See, in this case, we can also use hot concentrated nitric acid, because that hot concentrated nitric acid also generates sufficient amount of nitronium ion. However, we use nitrating mixture because it may be dangerous to heat concentrated nitric acid, and especially when you are carrying out nitration of hydrocarbons, one has to be careful. Okay, so we use concentrated nitric acid and concentrated sulfuric acid instead, which is a more safer way of nitrating. Okay, so of the two acids, that is concentrated nitric acid and concentrated sulfuric acid, sulfuric acid, you know, is more stronger as compared to nitric acid. Now sulfuric acid acts as the acid in this reaction and nitric acid acts as the base. The sulfuric acid protonates nitric acid in the following manner. This is the protonated nitric acid. Immediately a water molecule is lost and nitronium ion is formed. So the role of sulfuric acid, concentrated sulfuric acid in a nitrating mixture is essentially to facilitate the formation of nitronium ions. Okay, so once the nitronium ion is formed, then the reaction proceeds in the same manner, that is the nitronium ion reacts with the benzene nucleus, gives us the resonance stabilized carbocation, arenium carbocation, and finally loss of proton gives you nitrobenzene. Now the nitro group is also a deactivating group. Okay, so once the nitro group is introduced onto a benzene ring, it will not again react with a second nitronium ion. Okay, and there is no danger of there is no limitation attached to this reaction, that is polynitration does not take place as in case of other reactions. Okay, so this is about nitration. And nitro compounds, nitro aromatic compounds, you know, are very important, okay, in the formation of drugs. Many of the drugs like benzocaine, procaine, etc., they are painkillers, okay, and they have nitro compounds as the starting products. Nitro groups can be easily reduced to amino groups, okay, and amino groups have some importance of their own. So in this manner, that is why nitro compounds, nitro aromatic compounds are very important, and therefore we study this. However, I would like to tell you that it is not always that nitrating mixture has to be used as a nitrating agent. Depending on the reactivity of the aromatic nucleus, you can use dilute nitric acid also as a nitrating agent. You must have used for carrying out nitration of salicylic acid or for nitration of phenol, what do you use? You use 15% HNO3 or you use any dilute nitric acid and you still get the product, isn't it? Because there the nucleus is sufficiently activated because of the presence of certain groups like OH group. Is it very clear to you? So depending on the activity of the aromatic nucleus, you will use the nitrating agent. Another example could be given of nitrobenzene. If you want to carry out nitration of nitrobenzene, then concentrated HNO3 and concentrated H2SO4 will give you little yield of product. But suppose you use fuming nitric acid and concentrated H2SO4, you will get better yield of product. Okay, that is because nitrobenzene is deactivated. The benzene ring of nitrobenzene is deactivated as compared to the unsubstituted benzene nucleus. Is it clear to you? Okay. Now we proceed to halogenation. Okay. In case of halogenation reaction, how do we generate the electrophile? You have, if you want to carry out chlorination of benzene to produce chlorobenzene, the chlorine molecule is not sufficiently electrophilic in nature. Okay, so you have to add a strong Lewis acid like AlCl3. AlCl3 complexes with chlorine and you get a complex Now this complex reacts with benzene in a similar manner. So the pi bond attacks the chlorine and the sigma bond between the two chlorines is shifted onto this second chlorine and you get the formation of AlCl4 minus and the electrophilic chlorine is bonded to the aromatic nucleus and the rest of the reaction mechanism remains the same and you end up forming chlorobenzene. Okay, so in this in halogenation reaction the generation of electrophile is by using a strong which acid? Lewis acid like AlCl3, anhydrous AlCl3. Is that clear to you? Okay. Now we move on to the next reaction that is sulfonation. Now you know that sulfonation reaction is also a very important reaction. Okay. So in case of sulfonation, what do we use as a sulfonating agent? We use H2SO4, concentrated sulfuric acid. We also use a mixture of sulfur trioxide and H2SO4. That means excess sulfur trioxide is added to concentrated sulfuric acid so as to convert it to oleum. This mixture of SO3 and H2SO4 is called as oleum. Now it is found that the reactive species which takes part in the reaction is the sulfur trioxide itself. And sulfur trioxide, unlike other electrophilic substitution reaction, does not already have a positive charge on it. Now, so your electrophile is SO3. How does the reaction take place? Okay, this double bond opens up, attacks the sulfur atom. One of the double bonds shifts on to the oxygen and you get the formation of the arenium carbocation with a SO3 minus. Now why does SO3 have a negative charge now? Earlier when the electrophile, when the benzene ring attacked the electrophile had one electron less and it had a positive charge. Now the octet of sulfur is complete. So when a bond is formed with the carbon atom of the benzene ring, there is an extra electron associated with the sulfur and therefore it gets a negative charge. One more, so the intermediate has both positive as well as negative charges, unlike the earlier reactions in that we had only a positive charge on the benzene ring, but on the electrophile which was attached there was no charge. Okay, this intermediate is more stabilized as compared to the others, and also you know that the sulfonation reaction is reversible. The answer to that, sulfonation reaction being reversible, can be had from the ordinate diagram, reaction ordinate diagram. In case of a substitution reaction, it has to cross this barrier of transition state 2. It has to have, if this is the energy barrier for crossing, for the reactant to cross over to form the carbocation. Okay, and this is the energy barrier which is required by the carbocation to form the mono-substituted product. Now it is found that in case of sulfonation, the energy barrier which is required to cross over to form the mono-substituted product and the energy barrier required by the carbocation to go to the to undergo the reverse reaction, that is desulfonation reaction, is almost the same. Okay, so in other words this will be like this. Okay, so that this height and this height of the energy barrier is almost the same. So therefore some of the ions would cross over and form the mono-substituted products, whereas some of the ions would go in the reverse manner and form the reactant. So you find that sulfonation is a reversible product as compared to most of the other reactions which are involved in this aromatic electrophilic substitution reactions. Okay, so some strategies would have to be applied, like removal of water, etc., so that the reaction will go forward, so that the reverse reaction does not take place. Are you understanding this?
Yes.
Okay. And in addition, once the product is sulfonated, how is a sulfonic acid group? That is also a deactivating group, because the groups which contain double and triple bonds in them, they are able to withdraw electrons and involve them in their resonance. So they are deactivating groups. Okay, so such groups, when once you have introduced into your benzene ring, will not prefer to react with another SO3. Okay, so you don't have the problem of polysulfonation. Is that clear to you? Okay. Now we move on to the next reaction, that is Friedel-Crafts reaction. Okay. Now Friedel-Crafts reaction, this name comes from the names of two scientists who have discovered this reaction. You know when? In 1877. Okay, as early as that they had discovered this reaction. They were organic chemists and they were also interested in mineralogy. So that is how AlCl3 which has come into organic chemistry. Okay, so you know that suppose I heat a mixture of alkyl chloride and benzene, okay, for hours together or long times, the reaction fails to occur. Okay, unlike in our SN1 SN2 reaction where the reaction takes place instantaneously, there the nucleophile is a strong nucleophile. Are you understanding? There the nucleophile is something like OH minus. Here the nucleophile is a benzene ring. The pi cloud of electrons are actually belonging to the stable aromatic nucleus. So they do not react with a weak electrophile. So when this Friedel and Crafts added AlCl3 to a mixture of alkyl halide and benzene, immediately reaction took place. The reaction mixture became warm and a vigorous reaction started and HCl was given out. Okay, so how does this reaction proceed? Again, as we had seen in case of halogenation, this is my alkyl chloride plus anhydrous AlCl3 will give you the generation of an alkyl carbocation plus formation of AlCl4 minus, which acts as a base, and later it is helpful in the abstraction of this proton. Okay, the remaining two steps are the same, that is the alkyl carbocation will react with the benzene nucleus, that is the pi bond will open up and form the bond with the alkyl carbocation and you will get the formation of a alkyl benzene eventually. Now the problem with alkyl benzene is it does not stop at monoalkylation. What kind of a group is R group? Which type of effect does it exert on the benzene ring? It exerts a plus I effect, positive inductive effect. So it pushes electrons towards the benzene ring and makes the benzene ring more nucleophilic, more electron rich, and therefore it is more nucleophilic as compared to the unsubstituted benzene. Once it is formed, an alkyl benzene molecule is formed, that will react with the carbocation rather than the unsubstituted benzene ring reacting with the carbocation. Therefore, there is a problem of polyalkylation. Now to prevent this, what can one do? To prevent polyalkylation, what can you do? You can employ, stop the reaction at the, you can employ more amount of benzene. Don't use stoichiometric amounts of benzene and alkyl halide. Use more quantity of benzene. In this manner you will get monoalkylated product and you can recover the benzene and again carry out the reaction. Is it clear to you? So although this Friedel-Crafts reaction is wonderful in the sense that you can introduce a variety of alkyl groups onto the benzene ring, it has its own limitations. Like the first one I discussed was polyalkylation. Okay. The second thing is that if I want to carry out acylation of benzene, that is if I react the benzene with chlorobenzene in presence of anhydrous AlCl3, I will not get biphenyl. Or if I react it with vinyl chloride, we do not get vinyl benzene. Okay, what is the reason? Because the carbocations formed here are highly unstable. Is it clear? So for obtaining biphenyl, you will have to use some other reaction. Okay, there are other reactions like Ullmann reaction and others, but you cannot produce a biaryl using Friedel-Crafts reaction. Is that clear to you? Then the third limitation which is there here is that the alkyl carbocation group which is generated almost immediately rearranges to form the more stable alkyl group. Like if I start with N-propyl chloride, it reacts with AlCl3 and it generates N-propyl carbocation, and this N-propyl carbocation, as soon as it is formed, rearranges to give isopropyl carbocation. So eventually I will isolate the product that is isopropyl benzene and not N-propyl benzene. Is that clear to you? So unless the carbocation generated is the most stable carbocation, you cannot isolate an straight chain alkyl group attached to the benzene ring. Okay, you will always get the more stable rearranged carbocation attached to the benzene ring. Is this clear to you? So these are some of the problems which are or the shortcomings of a Friedel-Crafts reaction. Now there are some modifications of Friedel-Crafts reaction. Modifications are that you can use different alkylating agents. Like in this case, I have used alkyl chloride, they have used alkyl chloride. You can also use an alcohol like ROH. Only you will have to use a Bronsted acid like HF, okay, and it will lead to the formation of a protonated alcohol which will eventually lose a water molecule and lead to the formation of electrophile. Okay, the carbocation which acts as the electrophile. And the remaining steps will be the same, that is generation of the arenium carbocation and the loss of proton. Okay, you can also use an alkene as the alkylating agent. Suppose I use the simplest alkene. Which is the simplest alkene? Ethene or ethylene. I will have to use Bronsted acid and I will be able to generate a carbocation, ethyl carbocation. Okay, and this when reacted with benzene, on reaction with benzene, will give me ethyl benzene. So these are some of the modifications of the Friedel-Crafts alkylation reaction. Now next we move on to Friedel-Crafts acylation reaction. What is Friedel-Crafts acylation reaction? The reaction in which an acyl group is introduced into the aromatic nucleus. Now what could be the different acylating agents? Okay, so these are used along with AlCl3. Okay, again the role of AlCl3, anhydrous AlCl3 here is to generate an acylium cation. Once the acylium cation is generated, it will lead to the formation of this is the acylium cation. You can show two resonating structures plus AlCl4 minus. The acylium cation is attacked by the benzene ring. You eventually get a ketone. Okay, so if you have started with acetyl chloride, you will get acetophenone as the product. Okay, or if you have started with acetic anhydride, again you will get acetophenone as the product. Now here again the acyl group is a deactivating group. Okay, so therefore there is no problem of polyacylation as in case of Friedel-Crafts alkylation. There cannot be polyacylation. Okay, also no rearrangement of that acyl group takes place. Okay, so what is the advantage of this? If you want to prepare, let's say, N-propyl chloride, then you can start with propanoyl chloride. So you will get propanoyl benzene. Okay, and when you carry out a Clemenson's reduction reaction, the C double bond O group gets converted to CH2. Okay, so what do you get now? You get N-propyl benzene. In case of Friedel-Crafts alkylation reaction, the preparation of N-propyl benzene was impossible because the moment the N-propyl group is generated, it rearranges and forms isopropyl group. But here in this case, no rearrangement takes place and the reduction of the C double bond O will give you CH2. Is that clear to you? So this is how acylation reaction is carried out. Only in this case, once the acyl group is introduced onto the benzene ring, it still complexes with one molecule of AlCl3. Okay, so therefore more than stoichiometric amounts of anhydrous AlCl3 has to be added in this reaction. Okay, and you also know that to break the complex we have to add water to the reaction mixture. Okay, and in that process AlCl3 gets converted to AlOH thrice. So AlCl3 is not regenerated. Okay, but nowadays you have different catalysts. Okay, you don't have to use anhydrous AlCl3. You can use zeolite catalysts, you can use clay catalysts and a number of other catalysts, okay, which are reusable, which are not consumed in the reaction, or those which can be recovered, regenerated, reused. Is that clear? So I think with this I have covered the 5 important types of reactions which belong to this class of electrophilic aromatic substitution reactions. Okay. If you want to read more on this topic, you can refer to books like Jerry March, or you can refer to Morrison and Boyd, Paula Bruce, or Wade and Singh, and there are so many books which deal with electrophilic aromatic substitution reactions. So I think the mechanism of electrophilic aromatic substitution reaction was quite clear to you, and we will end the session here itself. Thank you.